Hi folks, this is Şefik. Today we are going to implement elliptic curve Menezes-Qu-Vanstone in Python programming language from scratch. But before we begin, please like the video and do not forget to subscribe to the channel to stay up to date with the latest videos. Also, your comments are more than welcome. Thank you for your all support in advance. Elliptic curve Menezes-Qu-Vanstone, or shortly ECMQV, is a key agreement protocol common with authentication, similar to elliptic curve integrated encryption scheme. Elliptic curves can be in many different forms. The most popular ones are Weierstrass, couplets, Edwards curves, and its variation twisted Edwards curves. But in this video, we are going to adopt elliptic curves in Weierstrass form. You can adopt couplets or Edwards curves in your implementation. Firstly, the equation for elliptic curves in Weierstrass form is y squared is equal to x to the its third power plus ax plus b. Let's take a note for this equation in our notebook. Y squared is equal to x to the power of 3 plus a times x plus b. This is going to be our elliptic curve equation. Thereafter, we are going to use addition formulas for Weierstrass curve. This is the addition formula if the points P and Q are different points on the curve. Let's implement this addition formula in our Python program. I'm going to create a function at points, and this is going to get P and Q points, and these are going to be tuples. Thereafter, I'm going to extract x and y coordinates of P and Q as x1, y1 for point P and x2, y2 for point Q. Addition formula becomes different if the both P and Q points are same point, as you can see here, but the just beta calculation is going to change in both point addition and point doubling. So in this at points function, I'm going to check P and Q points are same or not. If x1 is equal to x2 and y1 is equal to y2, thereafter this is going to be a point doubling, and for doubling a point, beta is going to be here. Beta is going to be 3 times x1 squared plus a and over 2 times y1. Otherwise, if P and Q are different points, we are going to calculate this beta value. Otherwise, beta is going to be y2 minus y1 over x2 minus x1. Once we calculated the beta value, thereafter we are going to use the same formula for x3 and y3 calculation for both point addition and doubling a point. Here x3 is going to be beta squared minus x1 minus x2, and y3 is going to be beta times x1 minus x3 minus y1, and this function is going to return x3 y3 tuple. Those addition formulas for elliptic curves are designed for real numbers. As you can guess, this division is going to be a float number. On the other hand, in elliptic curve cryptography, we are working on finite fields. In other words, all points are going to be integers for some modulos. So I'm going to append here an integer modulo p, and I'm going to move those denominators to numerators with its multiplicative inverse value. Here I'm going to change the sign to multiplication. Thereafter, find the multiplicative inverse of this value for modulo p. Similarly, I'm going to do it for this denominator. Find its multiplicative inverse value for modulo p. And finally, in x3 and y3 calculation, I'm going to find values for modulo p. Then let's decide the elliptic curve configuration for our experiment, and we are going to use the same elliptic curve with Bitcoin protocol, which is SECP256K1. In this blog post, you can find the required configuration values. We are going to use this curve, and a value in our equation is going to be 0 and b value is going to be 7. as mentioned here. Also, we are going to use this base point G, and this is going to be a public point. I'm copying this X and Y coordinate values for the base point G. G is going to be, this is going to be its X coordinate, and this is going to be its Y coordinate. Also, modulo and order. Order defines the number of points on our finite field. They are mentioned here. We are going to use those values directly. I'm going to say P for modulo and N for order of the curve. We can confirm that this point is going to be on our curve. Let's create a function. It's on curve, and this is going to get a point P, and also modulo P lowercase. Thereafter, I'm going to check this equation. Y squared is equal to x to the power of 3 plus a times x plus b. If this is satisfied, then this point P is on our curve. Of course, we have to check the both left and right hand sides for modulo P. Thereafter, this calculation might be greater than our modulo P. That's why I'm going to append P as third argument. It's going to find the x to the power of 3 for modulo P. By the way, we haven't assigned the x and y values. They are coming from point P. Let's check our base point is on our curve. Point G is on the curve, and this is true. This means that this base point is on our curve. Moreover, we already implemented at points function, and let's point base point to base point itself, and it's going to be point 2G. And let's see what point 2G is. We can confirm that this addition point is on the curve here. Let's call is on curve function and pass x3 y3 tuple and also modulo P, and recalculate point 2G. And as you can see, this doesn't return any error. This means that this point 2G is on our curve. Now I'm going to delete the calculation of point 2G and build a for loop for I in range from 0 to 20, and I'm going to create a temporary point, and its initial value is going to be base point itself. Thereafter, in this for loop, I'm going to call at points function and add base point to temporary point. And this is going to be temporary point's new value. Then I can start this for loop from 2, because I'm going to print here ig is going to be 10 point. As you can see, this is 2G, this is 3G, and finally this is going to be 19G. Let's find 9G. This value is on our curve and it's 20G. Here 20 is going to be my private key, and I'm going to find 20G, and this point is going to be my public key. Of course, my private key value is going to be a large number. That's why calculation of this point is going to be computationally hard. At this point, we have double and add method, and with this algorithm, we are able to calculate k times base point G much faster than a one by one calculation as illustrated here. And basically this algorithm represents the private key value as binary. Thereafter it applies doubling always for its all bits, but if the current bit is equal to 1, thereafter we are going to apply base point addition. As you can see, this bit is equal to 1 and we append the base point P to current calculation. But if the current bit is equal to 0, thereafter we are going to skip the adding base point. Now let's implement double and add method. Apply double and add method, and this is going to get a point G. This is going to be a tuple. Thereafter it's going to get a integer value k, and finally let's transfer the modulo. Here k is going to be an integer value, and we are going to firstly transform it to binary. Call binary function and pass k as input. This binary function is going to return a string with this pattern. Always its first two letters are going to be 0 and b. That's why I'm going to discard its first two letters. Start from index 2 to the end. Thereafter we are going to build a for loop for I in range. From 1, it's going to start from 1 because the first bit is going to be discarded. As you can see, there are 10 bits in this representation, but in the rows there are 9 rows. So we are going to discard the first one and go to end of the bits, and current bit is going to be I2 I plus 1, but this should not be comma. In this function, I'm going to define target point, and its initial value is going to be G itself. Here we are going to apply doubling always. That's why I'm going to call at points function and at target point and target point. Also, we are going to have modulo p argument as input, and this is going to be the new value of target point. Moreover, if the current bit value is equal to 1, thereafter I'm going to add the base point G here, and after this for loop I'm going to return the target point as a result. Now let's test this double and add method for some k. Our base point was G here, and let's calculate, for example, 20G, and our modulo P was P. As you can see, this is going to be our 20G value, and it's exactly the same value with this line. So we don't have to build a for loop and calculate the k times g one by one. The good part of this algorithm, this double and add method, no matter how large the k is, we are going to calculate the k times g much faster than the for loop. Here the light blue represents the double and add method, and the dark blue represents the for loop here we designed here. So if k value is really large, it's going to be hard to calculate it one by one, but we are always be able to calculate it with double and add method easily. This is called elliptic curve discrete logarithm problem, because suppose that q is the public k value and k is our private k and g is the public base point. If you know both k and base point g, it's very easy to calculate point q. But if you know both point q and point g, it's computationally hard to extract k, because you have to build a for loop as illustrated here, and it's really hard. So this is called elliptic curve discrete logarithm problem, and elliptic curve cryptography depends on the hardness of this. So we implemented point addition formulas and also double and add method successfully, and we built our elliptic curve, so I do not need this for loop anymore. And finally, in double and add method, we should check the target point is on the curve. Here I'm going to call isOnCurve function and pass the target point as input point p, whereas our modulo was p lowercase. Once curve configuration and addition law and also double and add method functions are ready, we are ready to perform EC-MQV. Alice and Bob will pick large integers as private keys. That's why I'm going to import random module, and firstly Alice is going to generate a private key, and let's store her private key in ka variable, and here I'm going to use random dot generate random bits, and recommended k size is 256. This is equivalent to 3072 bit RSA. Thereafter Bob is going to pick a large integer as his private key. Similarly, I'm going to store this in kb variable. EC-MQV also requires to generate random integer numbers, and these are going to be secret too. Alice is going to generate RA as her random key, and this is going to be 256-bit integer. Similarly, Bob is going to generate RB. Thereafter, Alice and Bob will find the corresponding points for this private case and random case. Let's store the public key of Alice in the QA variable, and we are going to use double and add method we just implemented to find the corresponding public key. Base point is going to be G defined here. K is going to be KA for Alice, and modulo is going to be this predefined value p. Similarly, she's going to find the random point, and I'm going to store this in RA uppercase. Here k is going to be lowercase array. Similar to her public key, this random point is going to be public too. On the other hand, random key must be kept secret. Thereafter, Bob is going to find the corresponding points for his private key and random key. Bob's public key is going to be his private key times base point g, and his random point is going to be RB, which is his random key times base point g, and I'm going to store these values in QB and RB uppercase respectively. Once they find their public keys and random points, they are going to calculate the signatures. To calculate signatures, we need to transform an elliptic curve point into an integer value. Here r is the elliptic curve point, whereas r bar is an integer value calculated from point r. This calculation is depending on value L, and L should be calculated with this formula. This requires to find the sail and floor functions respectively. Thereafter, here and is the order of our elliptic curve. Let's find the L in our implementation first. To find the logarithm, I'm going to use the math module. Thereafter, I'm going to call math.log base 2 of n. Here I'm going to call math.log, and I'm going to pass n as first argument and 2 as base. This is going to find the logarithm base 2 of n plus 1 over 2. Logarithm calculation should be for floor. Here I'm going to call math.floor. And finally, I need to find the sail of the final calculation. Math.sail. This is going to be L. Let's see the value of L for our curve configuration. That's 129. I'm going to define a bar function, and this is going to expect a point. As you can see, we just need its x coordinate. So here I'm going to find its x and y coordinates first. Thereafter, I'm going to find the x mod to the power of L. Bar value as x mod to the power of L. Then I'm going to add the value of 2 to the power of L. Here I'm going to append 2 to the power of L. And this is going to be my final value. This function will find the first L bits of the x coordinate of the point P. Now Alice is going to find her signature SA. This is going to be an integer value, and she's going to use her random key plus first L bits of its x coordinate of random point array times her private key Ka, and this calculation should be in mod n. Similarly, Bob is going to calculate his signature SB, and this is going to be his random key plus first L bits of x coordinate of his random point times his private key KB. SA is the signature of Alice, and SB is the signature of Bob. Here Alice is going to send SA to Bob, and Bob is going to his signature SB to Alice. Once they calculate their signatures, they can perform key exchange. Here we are going to need the cofactor value of our curve, and this is public value, and cofactor value is represented with h variable, and it's equal to 1 for the curve SECP256K1. Alice is going to calculate value J. JA is going to be cofactor times SA, this is her signature value, times, in the parentheses, Alice is going to use the public values of Bob. Firstly, random point of Bob plus bar value of this random point times Bob's public key value QB. JA is going to be let's find the this calculation first. We are going to use double and add method. Point is going to be public key of Bob, which is QB. K is going to be bar value of Bob's random point, and modulo is going to be P. Thereafter, we are going to add random point of Bob. That's why we are going to use add points function, and first point is going to be JA itself, and second point is going to be random point of Bob. Modulo is going to be P again, and finally JA is going to be, we are going to multiply this constant with already calculated point. That's why I'm going to call double and add method again. Here point is going to be pre-calculated JA, K value is going to be cofactor times signature of Alice, and finally modulo is going to be P. Similarly, Bob is going to calculate JB, and this is going to be cofactor times his signature SP time public values of Alice, random point of Alice plus first L bits of the x coordinate of the random point times public key of Alice. Here let's copy these blocks and replace A identifiers to B. Here the both J values Alice and Bob calculated must be equal to each other. As you can see, this condition is satisfied, and let's see the contents of the JA and JB. They are really same. Once Alice and Bob calculate the same elliptic curve point, they can use some K derivation function to generate K's from this point. Thereafter, those K's can be used for symmetric key encryption algorithms such as AES, and also for message authentication code, or shortly MEC. Message authentication code part provides the authentication, and symmetric key encryption part provides the secure communication. Now let's focus on the math behind of this key exchange. Alice did calculate the JA value, and let's copy it from here. In this calculation, I'm going to replace the random point calculations of Bob performed. Uppercase RB is equal to Bob's private key times base point G. Similarly, public key of Bob was calculated as Bob's private key times base point G. Here, both statements in the parentheses have base point G multiplier. That's why I'm going to move this base point G multipliers to the outside. Here the statement in the parentheses is exactly equal to the signature of Bob. You can remember this: Bob's random key plus x coordinate of his random point times his private key. So we can replace this statement to signature of Bob. And similarly, Bob does this calculation, JB. Here I'm going to replace the random point of Alice calculation, which was random key of Alice times base point G. Similarly, public key of Alice was calculated with Alice private key times base point G. Here I'm going to move the base point G multiplier out of the parentheses because both statements have base point G multiplier. And finally, this term is equal to the signature of Alice. We did this calculation in this line, so we are able to replace this to signature of Alice. As you can see, both JA and JB calculations are equal to each other, so this must be satisfied always. So in this video we implemented elliptic curve Menezes-Qu-Vanstone key exchange algorithm in Python programming language from scratch, and we also proven the math behind the key exchange algorithm. Thank you all for watching, and see you next time.